Friends, welcome to this channel. Today we will continue to explore vector sets, but this time we will zoom in a given detail of the implementation which I was handling in the latest days. So basically we saw it in the previous video about vector sets, this command which is called VRANDMEMBER with the name of the key, and it returns a random element from the vector set. This is very similar to the sets command as RANDMEMBER, and it is also similar in the fact that you can ask for multiple elements unique or for multiple elements that can be repeated. This is basically like a bingo bag. If the number is positive, every time I take an element from my bag, I will not put it back. Instead, if the number is negative, I put it back each time and I extract the new elements, so repeating elements are possible. What is less obvious about this command is that it's the only way right now in order to retrieve all the elements of a vector set. So, for example, this vector set has 3 million elements, and I can ask for them all. And in 4 seconds I can even output them to the terminal, given that with Ghosty it is so fast. There is an optimization in order to handle very large counts. Why? Because it will be extremely slow. At some point we will not have left elements. Basically in our bag will be again and again we will pick elements that we already picked, and it will be very slow. So this is optimized in a specific way, which is to seek to a random element just for the first element, and then since the elements are linked in a linked list, we just return linearly all the elements. So they will not be much random, but for very large counts this is an acceptable implementation. Otherwise we'll break the server for a very long time. However, you know that HNSWs are the graph data structure that I use in order to implement vector similarity and vector sets. So vector sets are based on a two-view data structure. One view is a radix tree, where the elements are basically indexed in a dictionary, and the other is the HNSW, where the index is not by element but by similarity. And among the two, it's much better to implement VRANDMEMBER using the HNSW than the radix tree, because it's much simpler and faster to get random elements. Before checking the implementation, I'm going to show you a very small Python program that I wrote to return random elements from the vector set, 1 million random elements, and then show the distribution about how many elements were hit 0 times, 1 time, 2 times, and so forth, and then do exactly the same with the Python random number generator, which is very high quality and it is much more fair from the point of view of the distribution. Then I tried to make Claude writing also the same script. The first time it wrote my script, it's 45 lines of code. This is 75 after so much trying, because normally when you ask LLMs to write a Python script, they write a monster of many hundreds line of code with many dependencies, even to do the most simple of the tasks. So this was kind of an experiment about trying to make it behave in some way. So this is the output, because it takes 1 minute to run this and it's very tiring in the video. This is the output of my script. This is against vector sets, and this is against the Python random number generator. As you can see, the distribution is not completely crazy. It's biased in some way, but it's not totally crazy. The bias can be seen more in the Cloud Python script, because at the end it prints how many elements they were hit at least one time. It's like 850,000 elements, which is the fire distribution. And you could expect, even if you do multiple runs of this experiment, this number to deviate a little bit, like a few thousands of elements, not 55 k elements. So yeah, there are some problem in the distribution, but it's a good enough distribution for this use case. And then we can see normally how do you basically do this kind of stuff. Let's see. No, I didn't want to do that. Okay, so basically this is a graph, like a small world graph, with looks like it's a graph with many small local connections, not much far connections. So it's the perfect case for this example. You want to obtain, when you select a random element from a graph, enough mixing, okay? Which means that if you start from a given element, you should do a random walk, which is long enough that you end in a here or here with the same probability. And normally in a good enough graph, it's sufficient to walk, to take a random walk of steps which are logarithm of n times logarithm of n. You can think at it as like the first, like logarithm of n being the steps that you need in order to escape from your local cluster. And given that there are also n local cluster, multiple local clusters, you then want to escape your local cluster logarithm of n times, in order to give you some intuition about this. It's not so simple to see why it is logarithm of n by logarithm of n, but let's think that in general we have local connections, so we in logarithm of n can just explore a local cluster and not all the graph. Okay, so we need to do it multiple times. However, that's not great, because if you look at this BC logarithm of 3 million by logarithm of 3 million, it's a fairly large number, and we want the implementation to be faster than that. If you need to do 200 non-trivial steps for large vector sets, and you can have vector sets larger than 10 million items, it's not fast enough. For example, we can also check how fast is the Redis implementation. You see, it's fast enough. It's let's test with pipelining in order to see the actual implementation itself. It's 50,000 commands per second, which is not too slow compared to the fact that the graph is big and we need to take steps and the cache misses and all this stuff. I wanted to avoid to make so much work, and fortunately the HNSWs have some quality that can be kind of exploited, which is the fact that they are multi-layer. So what I thought was, what about at each step descending the graph before reaching level 0 and then doing logarithm of n steps, just logarithm of n, just descending the graph using random links. So I take a random path here, then I go down, I take a random path here, then I go down, I take a random path, and then I do my search. And this is what I did, and the implementation is here. HNSW random node. So first phase, descend from max level to level 0, taking random paths. Note that we don't need a more conservative logarithm of n by logarithm of n steps for proper mixing, since we already descend to a random cluster here. It's not totally true, because in the HNSW we have structure, so taking random paths will not actually lead us to a total random place, but also this is why it is important to put comments. As you can see, this command clarifies why the implementation will do a given thing. Otherwise, it will be very hard for the reader of the code to understand this stuff. So it's extremely simple. The current node is the entry point, and at each step we take a random neighbor based on the number of links that this node has, and we go to a random neighbor, and then we decrease the level, and we do the same again at a lower level, assuming in a given level this node will have some neighbor. This is especially true for the top entry point node, and it is possible that this node is alone at this top level, so this check is needed. And then the second phase. At level 0, we take log the n steps by c. C is a constant 3 times in order to mix a bit more. But still, even if it is 3, we saw logarithm of 3 million to be this. It's 42 is not 2000 and more than 2000 what it was. And then we do the random walk, which is very trivial to do. Here I believe that there is potential in order to improve this algorithm here, which is to take a very small random walk at the top levels, and I will be doing that. So the implementation, as you see it, is good enough, but it's not perfect. Also, here there is an interesting thing. Imagine that you have just 2 nodes in your HNSW graph. What happens is that this count, the length of a random walk, will either be odd or even. And it means that it will return always the same element, basically, without this line here, because it's 2 elements, and one has the link to the other one and stop. So it's ping pong. It's 4. We start always from the entry point in a given moment, and we return A, or we return B if the number of steps will be odd. And this is not good. So we add to the number of steps 0 or 1 at random, 50% of probability of adding 0 or 1. And this makes it more fair for the case of two steps, of just two nodes in our HNSW graph. Yes, so I hope that this was a more interesting way to look at a vector set Redis command, where we also explored something about algorithm and data structures instead of just recounting how the command works itself. And I want to make a next video where I can try improvements to the command to see if the distribution that we get will improve. Thank you. Bye.